You've heard time and again that the goal of bonding is to satisfy the octet rule. However, we find many exceptions in nature. We are expected as AP students to understand and recognize the exceptions. One is boron. Boron has 3 valence electrons that we assign to it. Strangely, boron is stable with a total of 6 shared electrons. It's just what is observed, and we just have to acknowledge that that is often what boron does. So it's so good just with a total of 6 shared electrons. Okay, elements beginning in period 3 and below can exceed the octet. It doesn't mean that they do, but they can. All right, so here, sulfur we know, we assign 6 valence electrons. This is being bonded to 6 fluorines. Well, remember, we usually try to respect the 4 sides of the box around our element symbol. But how do we accommodate this? Try to just equally spread everything out so you can see the bonding and the lone pairs that remain if there are any. So since I have 6 fluorine, I'm just going to spread them out evenly. So 1, 2, 3, 4, 5, 6. All right. Now, I know that fluorine never exceeds the octet and only needs 1 more to be stable. In fact, all the halogens come in only needing 1. So I know these all are going to form single bonds. So if I give back, or just reorganize, each fluorine will have 3 pairs. Give this one back. But my sulfur, my goodness, now has 12 electrons on it. How can that be? Well, sulfur. Sulfur's valence, 1s2, or electron config rather, 1s2, 2s2, 2p6, 3s2, 3p4. How on earth, if these are the 3s, how and where can it be sharing all these electrons? Well, remember, beginning in the 3rd energy level, we also have the 3D. They are available. They are available for additional pairs to be shared. That's why beginning in period 3 and below, all of these first have electrons being placed in the 3rd energy level, so that makes these accessible to be able to be used. Okay, that would be the structure for SF6. Okay, but sometimes we can come up with multiple structures for elements that exceed the octet that give us choice. So how do we know which is the best structure, which is the final structure we're going to come up with? Well, if we go to sulfate, and I'm actually going to get a whole new piece of paper so I can show this clearly. Okay, so sulfate. Sulfate, SO4 minus 2. So, if we first construct sulfur, assigning it those 2 electrons, it immediately is coming in with 8. All right, so what I could do is coordinate covalent bond, giving and making single bonds with oxygen just from sulfur. And then sulfur is not exceeding the octet. So this is definitely one option. Okay, but what else could we do? Well, sulfur, again, being assigned those extra electrons because of that -2. Well, we know that sulfur, because it's in period 3, can exceed the octet. Okay, so what if we double bond with one of our oxygens? So what if we make a double bond out of electrons from oxygen and from sulfur? But then the rest we just make with sulfur's electrons. Well, that's definitely a possibility. And then we know that this will show resonance because I chose to put my double bond here, but it could have gone here or here or here, so it's going to actually alternate. So we'll have 4 different structures showing us that. Well, could we have 2 double bonds? I mean, could 2 of the oxygens double bond? And then we have 2 coordinate covalent bonds. Or, gosh, while we're at it, could we have 3? Could we have 4? How do we know? Well, that's where formal charge. We do a quick little calculation for each element within our structure. So we'll have a set, in this case of 1, 2, 3, 4, 5 values. The structure that is preferred, the structure that we're probably going to find in nature, has the set of formal charge values closest to 0. In your packet, here is the definition for formal charge. We find formal charge by taking the number of valence electrons that we would assign to the element from the periodic table, minus 1/2 the number of electrons that are shared in bonding on the element, minus the number of lone electrons. And I will show you plenty of examples. Okay, so let's go ahead and calculate the formal charge on this sulfur. All right, we assign it 6 valence from its position on the periodic table. Even though we assigned an extra 2 because of this, that's not part of the calculation. 6 from its place on the periodic table, minus 1/2 the number of electrons that are shared in bonds, 2, 4, 6, 8, minus the number of lone electrons, which we have none on that sulfur. So the formal charge on this sulfur is 2. Let's now calculate for oxygen. Do we see that all of these oxygens are bonded the same? A single bond to sulfur with 3 lone pairs. So the value that I get for this will count and represent this oxygen and this one and this one and this one. Let's dig in. 6 valence is what I would assign, minus 1/2, 2 electrons are being shared, minus 1, 2, 3, 4, 5, 6. This gives a formal charge value of -1. So I have 4 -1s and 1 +2. It does not matter the order that you display them, just that they're all correct. So of my -1, -1, -1, -1, and 2. Ideally, we would like these to be 0, 0, 0, 0, 0. Now, I must say, these need to add up. If it is an ion, these need to add up, if you've done them correctly, to represent the charge of the ion. So, I mean, ideally, all of them being 0, that'd be for a neutral compound. But Here, they should equal -2 because we have an abundance of 2 electrons in our structure. So let's dig into this one. Okay, this sulfur is bonded differently than that one. We sign it 6 minus 1/2. 2, 4, 6, 8, 10 are how many? Minus 0 that are alone. So a formal charge of 1. Okay, now from the perspective of sulfur, we're getting closer to 0 compared to 2. So this is a little bit better of a structure from sulfur's perspective. All right, the formal charge. Now, this oxygen is different because it's double bonded. We don't have any double bonded here. So it'll be 6 minus 1/2, 4 minus 4, my lone. 0. I have my first 0. And the formal charge of these oxygen will be the same that I found up here. So here are my set of formal charges. I have 3 -1s. I have a 0 and a +1. Still, they accrue to be -2. This would be more preferred than this. So let's go to this structure. All right, I have 2 double bonded oxygen. So that will be the same as I calculated here. I have 2 single bonded. That will be the same as I calculated in the very first structure. So I'll go ahead and put my -1, -1, and then I have 2 zeros. Okay, let's see what the formal charge on this double bonded, single sulfur is. So 6 minus 1/2, 2, 4, 6, 8, 10, 12. And no lone. Ooh, 0. So far, this looks so much better. Again, we're going to add up to be -2, but I have 3 zeros. That collectively is much better. Could we have 3 that are double bonded? And then 1 that's single bonded. All right, well then, the only new formal charge will be on this double bonded sulfur element. So I have 6 minus 1/2, that would be 14. 2, 4, 6, 8, 10, 12, 14 that are being shared, minus 0, and that is a -1. So here I'll have -1, because I have my single oxygen. I have 3, and then a -1 on the sulfur. Okay, so what about 4 double bonds, just to go through this? Well, that's going to give us 0, 0, 0, 0, and a -2 as my formal charge on sulfur. This -2 is seen as worse than 2 -1s because one of them has moved 2 positions away from 0 versus 2 only being 1 position away from 0. So even though I have 4 zeros, because I have that one -2, that definitely makes this structure impossible. All right, so which one? Because we have a tie of formal charges. Well, whenever you have a tie, whichever has more negative on the more electronegative. So here is a -1 and -1, 0, 0, and here my sulfur is 0. But here it was 0, 0, 0. The sulfur is -1 and -1. We know oxygen is more electronegative, so the -1 should be on both of these oxygen, not on one oxygen and one on sulfur. So this is the winning structure. This would properly be shown resonating. So I would have to alternate and show my double bond up and down, and then the single, and have my 2 pair and 3 pair. Now, this is showing us a lot, ladies and gentlemen. And then I would also have to show it alternating between the right and the bottom. Yeah. I'd have to show it alternating between the left and the top. And, oh golly, the bottom and the left and the top and the right. Whew. There's a lot of structures here. What did I say? The bottom and the right, and then also the top and the left. Whew. That's a lot. That's a lot. That's a lot. That's a lot. The point I want to show is that we definitely resolved that on our sulfur there's going to be 2 double bonds to oxygen and 1 double bond. We know this is it because of the set of formal charge. And wow, this was an overwhelming example because it also involves some resonance. But hopefully we're understanding how to come up with our formal charge values. And we would say this is the preferred structure because the formal charge values are collectively closer to 0 and negative values on most electronegative elements. All right, that's formal charge.